Right, so let's continue talking about fluids and particularly fluid dynamics. We just got done talking about fluid statics, and the last lecture I talked to you a little bit about Bernoulli's principle and kind of an intro to fluid dynamics. What I want to do for the rest of the semester, I'll cover the notes today. I've just posted these on Blackboard under chapter 12 notes. So you have access to them. So I'm going to cover the notes today, hit the high points, what I think is important. And on Friday, I will do a couple of sample problems for you from this chapter, and then we'll be done. My plan is on Monday, which would normally be our last day of class, I'll post the third test. It's going to just be a sampling of everything that we've covered since test 2. So mostly things about energy, a few things about fluid dynamics, a few things about torque. So it shouldn't be anything really heavy. Expect a format very similar to exam 2, where you'll have quite a few problems that will come directly from the homework, and then 1 or 2 that I'm going to expect you to work out and email to me. So like I said, I'll post that on Monday, and I think I'll give you a week to do it, which would be about the time we would normally be scheduled to do a final for this class. Again, I typically don't do final exams because I don't really find that they make all that much difference in your final grade. Remember, I'm always looking at how well you're doing on the homework and how much you're engaging. So that certainly is going to play in to your final grade as well. So let's talk about fluid dynamics now. So remember, we talked about fluid statics, which is kind of our basic idea of pressures. You got Pascal's law. That's probably an important one to know, right? That Pascal's law says that if you apply pressure to a fluid, that the pressure is equal everywhere in that same fluid. So what we're going to look at now are fluids in motion. So if we take a look at the first image here, you've got a bunch of firefighters in there, spraying water on a fire or something. And what they want you to look at in this image is the idea that there are a lot of different fluids, right? You could model the smoke as a fluid if you wanted. You can certainly model the water as a fluid. You can look at the air in their packs as a fluid. Even the fire on this car over here, you could model it roughly as a fluid as far as how it moves and the flow and things like that. So that's what we're going to look at, is kind of how you build those mathematical models to describe what's going on. For example, if you were to look at the scene here, you can already kind of visualize and understand that even though we can say the water is a fluid and we can say that the smoke is a fluid, they're going to behave differently. They're going to be similar in a lot of ways. They're going to flow. There's going to be a relationship with pressure and velocity and that kind of thing. The densities are going to be different. They're going to behave different thermally, but we can still kind of model them as a fluid. And so we're going to look at kind of how we go about looking at those different properties. Oh, come on. So one of the things that we need to talk about in terms of fluid dynamics is something called flow rate. So anytime you hear the word rate in physics, you're talking about generally some quantity per unit time. We think about velocity as a rate, right? Velocity as a rate, it's a distance per time. Acceleration is a rate. It's a velocity per time. Well, with fluid dynamics, we talk about what's called flow rate. This is going to be a volume over time. So this is something like, let's say that I have just a water fountain out in the hallway, and I press the button to get some water. That water is going to come out of there at a certain flow rate. Let's say we had a gallon milk jug and we tried to fill it up with water from the water fountain. That's going to take several minutes to do because the flow rate out of the water fountain is going to be, every time you push the button, let's say you push and release, you're going to get far less than 1 gallon. And it's going to come out of there relatively slowly, so it takes some time. However, if we took the same milk jug and instead we went down to the local fire department and we turned on the hose from the fire truck, that's a lot of water coming out really fast, right? So that's a high rate of flow, and it's not going to take long to fill that water jug. Well, that rate of flow is dependent on a couple of things. Predominantly, it depends on the area of the tube that you're flowing through. This is why you see things like fire hoses tend to have very large diameters and large cross-sectional areas because they're intended to have a whole lot of flow at a given time. But remember, velocity and pressure have a relationship, and that's affected by the area. So if you've ever played with, say, a pressure washer, you have a lot of volume of water. It's got a high flow rate, but it comes out over a very small area. And remember, pressure is force per unit area. If we decrease the area, we keep the force constant, then our pressure increases. So we use all those things, and we take a look at this diagram. So we have some cross-sectional area. Let's say we have a circular tube, and its cross-sectional area is A. And we look at some distance, the water flows. So this is our cross-sectional area. Come on, where's my cursor? Here's my cross-sectional area A. And we're going to take some arbitrary distance D, and we're going to push some volume across there. Now we know that it's going to move with some speed, some velocity V. And we know that the velocity we measure is this arbitrary distance over however much time it took, right? We also know that flow rate, we're going to call flow rate capital Q. Another of those weird physics things where we use the same letter for different things. You also see Q as generally heat or heat energy. In this case, we're using it to indicate flow rate. You will see this kind of equation again in electricity when you do physics 2. We talk about something called flux, and that is a rate of current flow per time. And it's going to look very similar. It's going to be related to this surface area. But for now, we're going to assume that we have just a standard kind of circular surface area, and we have some standard distance. And we're going to define our flow rate as volume per time. It's a rate. A rate of what? It's a rate of how much we're getting. So volume per time. We know, if we look at this equation, Q equal V over T, capital V is our volume, T is our time. Well, what's volume? Volume, remember we did this in the Bernoulli problem. If area is length times width, and volume is length times width times height, then we can substitute length times width to be the area. And so the area times whatever that other dimension is must be volume. Thus, we can replace volume with area times distance here. We didn't do anything with time, so we get area times distance over time. Well, that's interesting because I've already defined that distance per time is velocity. So I can do another substitution and I can say distance over time is velocity. And we find that the flow rate of some fluid is equal to the cross-sectional area that the fluid passes through times the velocity it passes through. So this explains the pressure washer problem, right? If, let's say that we have a set, or let's say that we have some velocity, right? The water fluid, whatever it is, flows through a particular opening at some velocity. And our flow rate is going to be constant. I can only pump so much water into this hose at any given time. So let's say that's a gallon a minute, just for the sake of argument. Well, if that's a constant, and this is an equation, we end up with something that's like Q equal AV. Bernoulli tells us that must be constant. So if Q is a constant value, and we change one of the variables on the other side, that means they must have an inverse relationship. It means if one goes up, the other must go down. Or if one goes down, the other goes up. So in the case of our pressure washer, if we start constricting the hose, if we start making the aperture that the water flows through smaller and smaller, that means our area gets smaller and smaller. So area decreases. But area times velocity has to be Q all the time. So if area goes down, velocity has to go up. So that explains why in our pressure washer, if we make the aperture smaller and smaller, the velocity of the fluid has to increase, which again, we showed with Bernoulli's equation the other day. Now you can easily relate this if you take it a few steps further. Once you know that velocity, and you would like to know how much force that exerts. In other words, could I use the fire hose? Could I use the pressure washer to move a person around? Could I move a basketball with it? Could I move a baseball with it? Could I move a mountain with it? Well, that depends, right? That depends on pressure. Pressure is a function of force. Force is a function of acceleration. Acceleration is a function of velocity, right? Acceleration is velocity per time. So let's say we find the velocity from this hose, and we set velocity equal to, well, if acceleration is velocity per time, and we want to find acceleration is velocity times time. So if we say we know the velocity, we know the time, then we can find the acceleration. The other way you could do it is with momentum, right? Momentum is mass times volume. If we know what the mass of the water is, which is a function of its density, then we can find the energy, right? And if we know the energy, then we can go to our kinematic stuff. We can go to our kinetic energy plus potential energy formulas. We can do all kinds of things with this. So this is a really, really useful thing for you to understand, is what flow rate is and how it is related to area, distance, time, velocity. This is just a different way of doing Bernoulli that I did the other day. Notice that we have some constriction, we have some area, we have some distance, some velocity, we have a constriction. That means that the area has to change, the distance has to change, velocity has to change. A different application of the Bernoulli principle. You've probably experienced this before. So let's say we're driving down the interstate and we pass big giant 18-wheeler. If you get pretty close to this thing as you pass it, you can hear and feel the change in air pressure. You can feel the change in drag against the car. Here's why. Notice that if we're driving, let's say we're in the pink car and we're driving the same direction as the truck, we have P naught is the outside air pressure, right? That's the pressure on the other side of the road. That's not going to change. We have some relative velocity that we're traveling into the wind. But look, if we get close, then we have changed the distance between the two vehicles. We've created a constriction. This gives us the Bernoulli effect again, right? This is called a Venturi. So we create a Venturi. We know that this velocity has got to increase. And we know that that forces P1 to decrease relative to P0. So we have now a low pressure area in between the two vehicles. So what does that mean? That means that the closer you get, the lower that pressure is going to be. So you're going to get more of a push from the outside air pressure and potentially could draw those two vehicles together. So why doesn't that happen? Well, a couple of reasons. Generally, you're not going fast enough, and you're generally not traveling close enough to the other vehicle for it to matter. And the mass of the vehicles, the inertia that we have to overcome just from the difference in the air pressure is pretty high. Plus, remember, we have to deal with the friction of the tires against the ground, that kind of thing. So this is why you generally don't see collisions where cars pass trucks and they get sucked into each other. A place where you will see this principle in action on purpose is if you ever have seen a stock car race, like NASCAR. They do a thing called drafting, where they will intentionally drive with one driver effectively has his front bumper within inches of the back bumper of the guy in front of him. So what he's doing is he's using the advantage of Bernoulli's principle. He's using that Venturi back there. What he's doing is using the other car as a wind block. So that other car is taking all the drag. He's having to expend more energy, where the guy behind can come off of the gas pedal a little bit and stay at the same speed. Now he's got extra power. He's got extra speed. So if he needs to pass, he can do that. I know if you're not a NASCAR fan, you may not have ever seen that. And if you don't really care, that's cool. But I'd say go out and at least take a look on YouTube and look at some race cars going around the track. And it's pretty cool what you'll be able to see now that you understand a little bit about physics. I'm not a big NASCAR fan either, but I do like the physics behind it. So we use a lot of different things, use this kind of principle of creating a Venturi. One of them is this idea, this is an old perfume bottle, right? So this is also, if you have like a spray bottle, Windex or something, it works the same way. You have some fluid, you have a tube, and you have some sort of piston, some sort of squeeze bulb. So when you squeeze that trigger on the Windex bottle or squeeze the bulb on the perfume bottle, what you're doing is expelling the air out of this tube horizontally, which causes a low pressure area. It's low relative to the air pressure inside the bottle. The air pressure inside the bottle presses down on the fluid, forces it up this tube, goes into the vacuum, and picks up the exit velocity and gets sprayed out. So this is your atomization. Just different ways to do that. Here's the airplane wing that I was talking about the other day. And we can see that we can change what's called the angle of attack on the wing and change the airflow a little bit. This is a barometer I was talking about. Don't care about that. Okay, so here's an interesting one. So here we have this fire truck, and we're about 10 meters off the ground. Well, the water has to go uphill, basically, right? Because you got the water stored in the truck. So how the hell do we get the water up this 10-meter wall? Well, in order to do that, we have to induce kinetic energy, which means an increase in pressure. So effectively what you've got is a pump inside the truck that increases the pressure on that fluid, in this case, the water, such that it is higher than the outside pressure or the pressure inside the hose. Thus, you can spray the water uphill. And rescue the kitty cat, I think, is up there. So with smoke, it looks a little different. The density of smoke is different than that of water. So what you can see is if you look at the smoke come off a candle or something, it's gonna be pretty smooth as it goes up. This is what we call laminar flow. So if something is very, very smooth as it flows across the surface, that's a laminar flow. Now, things are going to happen. For example, as this smoke rises, obviously it's got mass, the particulates in it, they're going to slow down, they're going to be more affected by air currents, and they're going to start moving around. And that's why you get this behavior that you see at the top of the smoke. And this is called turbulent flow. There's a whole area in fluid physics where engineers try to determine the boundary between laminar flow and turbulent flow. Obviously, laminar flow is mostly more desirable, right? Because you're not having to deal with friction. You're not losing energy to things. So you'd like to keep flows as laminar as possible in most cases. And that's going to be a function of a lot of different things: velocity, temperature, pressures, that sort of thing. So like I said, there's a whole field of study that you can look at. This is another great example of laminar flow. So if we have laminar flow, let's say that in section A here, this is maybe water flowing over a riverbed. And it's going to have different layers. Now, these layers are going to be separated usually by some density. If you're a geologist, you probably look at different types of rock, and you know that different particulates will float at different layers. Well, as long as those things do not mix, you can have these stratified layers of flow. So this is an example of laminar flow. In laminar flow, there's very, very low friction between the layers. However, once the friction between the layers increases, then they start to interact with each other because that's how friction works. And you get these kind of tumbling eddies, so you get this turbulent flow. So this happens, here's our riverbed. We got the water flowing nice and smooth. Nice laminar flow, but then there's a rock or something, and there's some inequality in the surface and the bottom, and you'll start encountering different friction. The internal drag, the drag between molecules, the interaction between the molecules of some fluid is what we call viscosity. High viscosity things tend to flow very, very slowly. They have a very low rate of flow. And low viscosity things, because they have low internal friction, can have a high rate of flow. The way I like to model this is, let's say that you're in your dorm room or a classroom or something. And that room is completely full to capacity. You're standing shoulder to shoulder, you barely have space to move. And suddenly there's a fire or something and everybody needs to get out. There's only one door to the room. Everybody's going to run to the door at the same time. There's going to be a whole lot of interaction between the people in the room, right? There's going to be a lot of friction. There's going to be a lot of collisions if you model the people as particles. So the rate at which people are going to leave the room is going to be relatively low. Everybody's trying to get through the door at once. The room is very full. What if we take the same room and we put two people in the room? Even if they're on opposite ends of the room, there's very little interaction between them. So there's very little friction. Now I have the same scenario. There's a fire. Everybody has to get out. Everybody's going out through one door. The rate of flow out the door is going to be significantly higher for the room that only has 2 or 3 people in it than it will for the room that is densely crowded. So that is a good model for you to think of viscosity. You might hear the term viscosity if you watch TV and there's an ad for motor oil all the time, likes to talk about viscosity. This is important in engines. You need oil that lubricates. So you need the oil to reduce the friction between your metal parts. If that viscosity is too high, then those 2 gears will not turn. Those metal parts won't move at all, and that's bad. If the viscosity is too low, then the oil moves through so fast that it does not. Doesn't lubricate anyway. Anything, might as well be air. Things that can affect viscosity, obviously, since viscosity is a function of density, density is affected greatly by temperature. Because density is a function of volume, volume is a function of temperature. So as the temperature decreases, things get closer together, right? If I take the temperature in the room and I make it cold, everybody's going to come closer together because they want to stay warm. If I make it hot, everybody's going to want to spread out to stay cool. Well, as your engine heats up, it causes the molecules in the oil to separate because they're getting hot. And it causes the viscosity to decrease, making the oil less effective. So that's what you'll hear about a lot of times on ads for AutoZone going, oh, come buy this particular kind of oil because it's very resistant to viscosity breakdown. Meaning you can operate it in a big wide range of temperatures and it's not going to matter. Most of the time, that doesn't matter unless you're operating a very specialized engine that operates at very, very high or very, very low temperatures. For your car, generally the generic stuff you can buy off the shelf at AutoZone is fine. So here's some laminar flow between a couple of plates. There's a great video. If I can find it, I will post it. Dustin Sandlin, the guy that did the video I posted about dropping cats, where you can see the torque and everything. He does a really, really great video about laminar flow and gets really, really deep into the mathematics of it. And he nerds out about it a little bit. It's pretty awesome. If I can find that, I'll post it for you just because I think it's interesting. As an example of viscous and non-viscous fluids. Oh, okay. So this is kind of interesting. Let's say you have your neighborhood and you need water in your house to run showers, bathtubs, washing machines, dishwashers, sinks, all that kind of thing. Well, there's a limited amount of water supply in the waterworks, right? In the city water processing facility. And so you got this big giant pipe, that's your main, It goes out to individual houses. Well, if everybody uses the water at the same time, then the pressure decreases. If everybody were to flush the toilet at once, then you would see a decrease in water pressure all over that particular system. Now that sounds silly, and it sounds like a whole lot of people that would have to flush toilet at the same time, and it is, but this has actually happened. Anecdotally, there was a TV show back long ago, probably before most of you were born, called MASH. Really, really great show. If you've not seen MASH, I highly recommend it. It was about a hospital in the Korean War. The series finale of MASH aired in like 1980 or 81, I can't remember. And it's a matter of historical fact that many, many large cities experienced a decrease in water pressure that correlates exactly with the end credits rolling of the last episode of MASH. Because everybody was watching this thing and everybody was waiting for it to end before they went to the bathroom. And so you cause a decrease in pressure. This is also the reason that there are water towers all over the place. You probably thought they were for storage. They are not. Water towers exist to create pressure. Remember, pressure is a function of force. Force is a type of energy, particularly our potential energy in this case. So if we have a mass of water in this tower and we raise it up really high, potential energy, remember, is mass times acceleration of gravity times the height. So we take a bunch of water, we put it on a really tall tower, we connect a pipe to the bottom of it with a relatively small diameter, and we run it to our water main. So what does that do? It gives us pressure in the water main. So you have your reservoir that's feeding the supply, but you have these towers periodically around town, and they produce pressure. So that even if everybody in the neighborhood is watching MASH, when they get up to go to the bathroom, the toilet's still going to flush because you have the excess pressure from the water towers. That would be kind of a fun question, I think, to put on the test. Your body works the same way. Your lungs and your heart work on differential pressure. You know, you've got your heart, for example, does diastolic and systolic compressions. And so when it squeezes, it increases the pressure inside the heart, which causes blood to squirt out, go through the arteries. And as it retracts, or as it releases, that creates a lower pressure area and causes the blood to flow back in. You have little check valves in the heart that have your one-way flow. Those are your mitral valves, if you guys are medics. So here's the transition boundary I was talking about. This has to do with aerodynamics. So you can see an example of laminar flow becoming turbulent flow. And in aviation and aerodynamics, this is drag. So you would like this, right? You would like for the flow to be laminar. This is bad because you're not getting that flow over the wing. And if you're not getting the flow over the wing, you're not creating the pressure differential and you're not creating lift. And the airplane falls out of the sky like a brick, which is sometimes desirable and kind of fun. Talk about buoyancy. This is another good one to look at. I may do an example of this Friday. Let's remember when we were doing falling objects at the beginning of the semester, we generally ignored things like air pressure. We assumed everything was in a vacuum. Well, now we have enough information and we have enough knowledge of physics that we can account for air pressure, at least rudimentarily. And the way you do this is not that hard. What you do is you take the mass of your object and you find its velocity. Well, at some point, you know that as it falls through this fluid, this air, there's going to be a buoyant force, right? And so what you can do is you can measure the density of the air, you can measure the mass of the air, and you can find the point at which the pressure, the force created from the object falling as a result of gravitational acceleration is equal to the buoyant force of the air, at which point the object's going to stop accelerating and it will fall at a constant rate, a constant velocity. That's what we call terminal velocity. So this is why when you drop something, it does not continue to accelerate forever until it hits light speed. There's a drag force that comes from the buoyant force. It comes from this turbulent flow. And at some point, that drag force is going to equal the force of the object falling under acceleration. And so you get terminal velocity. This is how spacecraft work. When we re-enter the atmosphere, we use this idea of drag force to slow down. The spacecraft comes in at tens of thousands of miles an hour because we're out in the vacuum of space. But as soon as we hit the atmosphere, we need to slow down. We have to slow down significantly before we deploy parachutes. Otherwise, parachutes come apart, and what's the point? So what we do is we build the spacecraft in such a way, generally these kind of cone shapes, where we create a bunch of drag. We create a bunch of buoyant force. Well, of course, we're trading energy, right? So we're going to turn that energy into heat energy. That's why it gets very, very hot. But what happens is we slow the vehicle down. Now, that is a very, very complex problem because the vehicle is re-entering the atmosphere where the density is very, very thin. And then as we get lower in the atmosphere, the density increases and it's not a linear increase. So that becomes a pretty nasty problem to do, to find out exactly what the angle is such that you can slow down enough to deploy the parachutes to land at a particular spot. But it's using exactly this principle. Look what this is. It's just a sum of the forces problem, just like we did before, just like we did at the beginning of the semester. Remember, Newton's second law is your friend. The sum of the forces is always equal to the total mass of the system times total acceleration on the system. Now, what the sum of those forces are, as we've seen, that's a combination of a lot of things, right? It's pressure, it's velocity, it's a cannon, it's something, right? Something is imparting energy. So you're getting force. Let's see. Yeah, what if it's not constant? This is called random walk. I'm not going to have you do these kind of problems because they're gross. Random walk is important to me as an astrophysicist because this tells me something about the life cycle of a star. Basically, what we're looking at is if we have some particle, let's say here to start, and this particle moves in a known density of a fluid, no matter what direction it starts in, it's going to hit another particle and it's going to change direction. And then it's going to do it again and again and again. Well, there's no guarantee of what direction you're going to move. There's no guarantee of the different masses of the particles. So it's going to go in random directions. Now, over a certain period of time, that particle will absolutely go from point A to point B over this distance X here, but it ain't gonna be linear. So it's random. And that random walk that we call it is a function of density of the fluid. And what we can do, particularly in astrophysics, one of the things we do is we look at stars and we determine the density of a particular star and we determine its radius. So if we know a density and we know a distance, we can apply a random walk function and we can find out how long it takes for one molecule of hydrogen, let's say, to escape from the core of the star all the way out, thus decreasing its mass. Well, that's one molecule. So what happens? We have billions and billions and billions of molecules. Over time, that means the star gets less massive. And this is how we calculate the age of things in astronomy. Just a different idea of random walk there. Trying to find something a little more interesting, I think. It's going to be it. Great. Yeah, okay. So that is the end of that chapter. Like I said, I posted these online. I'll work through a couple of sample problems for you on Friday, and then there will be no lecture on next Monday, and I'll throw up the last test for you, and you can have a week to work on it. As usual, you know where to find me if you need help. So I will see you guys in the next lecture.